Okay, we want to have, we don't need this line. Let's instantiate this first. And inside the post compute, we can do the forward filling and whatnot. So for inst and self-inst, we will do this two logic. We will also use this line. So this is already made available to us inside this. So we'll be using this variable. Since we already checked that the close is greater than equals to 0, the only thing we are left with is to check that the alpha is not null. And that's pretty much all we have to do here. For the signal distribution, we will do something similar. Okay, so forecast equals to that. So this is actually what we want to do. So forecast inst equals to this particular value. We can just use the same forecast and forecast chips, and this should implement the same logic. So again, this is just 30 lines of code, and it's doing the same thing as it's 90 lines of code because we are reusing this alpha implementation. So let's go ahead and see whether these two are the same. Let's verify that our implementation is accurate. Okay, so let's just check here. And while we are checking the accuracy of that, let's not waste our time and just do the same thing for alpha 3. So go here, we'll do this, inside the pre-compute. Let's compare this to the alpha 3 apply class. So what we did was over here, so let's just copy this. And then let's just join it over here. Okay, so this is our alpha computation inside the pre-compute. Inside the post-compute, we will do the forward fill, and the eligibility test is basically the same. For the signal distribution, this will be 1, 0, 1, 2, or 3, and there's not much to change here. So this is the same as before, and we have 1, 2, and 3. So this should also do the same thing as sorry, and we'll check whether the implementation is accurate. But first, let's go into we're running alpha 2 files, so let's see whether that is good. So we see that the both the ending capital is the same and the two data frames are identical, so our code is accurate. Let's try for the third alpha class. So, okay, we'll do this here. So anyway, our implementation is now a lot cleaner, right? For each of these alpha classes, all we did was specify some pre and post computation of the logic, and then we can compute our backtest statistics. And we will make this a lot more powerful going forward into the future. But we will first see exactly how to improve the current model. So one of the more rigid problems that we have now is that we're fixing to the entire, to the portfolio leverage. The portfolio leverage is always 1. And later you will see that this is an inadequate measure of the portfolio risk. And we'll explain that in the next lecture. So let's just wait for all of the back tests to run and verify that our code implementation is accurate. Okay, so both the implementations are once again identical, so that is great. At this stage, let's just so we don't need these three anymore because they're exactly the same. So let's make a directory for old code. And let's just move this into the old code. So that's pretty good. We don't need this anymore. And we can run each of these three strategies using the combined alpha classes. So moving on, we will look at how to extend this quantitative backtest to account for different levels of risk exposure, as well as how to combine the forecasts from the three different strategies. Because if you're working with a portfolio, you're going to have multiple strategies, and the different strategies are going to recommend different actions about each particular instrument. So we're going to combine the forecasts using the same alpha class, and this will allow us to then evolve into the more advanced model, which we will call the Russian ball model. So I'll see you in the next lecture.